Hello, and welcome to the senior design video for Project 22097. Our sponsors include NASA and the Simpson family, and our mentors are Dr. Sergey Shkraev and Dr. Jagan Tenga. Our team includes Haoming Yan, Martin Grant, Stephen Lingle, Daniel Keitel, Carlos Montiel, Darren Eggert, Bruce Bai, and Andrew Reynolds. The goals of this project were to further the research into building a low-cost, long-endurance, high-altitude UAV. This included the addition of solar panels and calculated flight paths that allow the vehicle to harness energy of the sun to increase endurance. The vehicle was also equipped with a high-altitude release system from a large weather balloon and an emergency parachute system. This video will highlight how our team went about the building and testing processes that enabled us to achieve our goals, and have a little fun along the way. But it wasn't all fun and games. Many long hours were spent with our mentors in the design process to ensure our calculations and theories were correct. The primary component of interest on our vehicle is the integrated solar panels that sit on top of the wings. This proved to be a challenge for our team of aerospace majors that have a limited experience in the electrical field. With a little practice and a steady hand, our team was able to construct the solar cells, implementing bypass diodes to ensure stability of the system. The area of the solar panels extend 2.43 square feet. They are wired in series to limit the current to 6 amps while reaching a theoretical maximum of 8.4 volts. A battery charge controller was integrated to allow the storing of power while in flight. A monocoat film was installed over the top of the panels to ensure protection from the environment. After double-checking our calculations, we were ready for in-house testing of our initial design of the release mechanism, which was a success, although room for improvement was noted and implemented before our next phase of testing outside on the bridge of the AME building. After the team was satisfied with the testing results and repeatability of the system, it was more permanently installed, utilizing a 3D printed case for protection of the lock. The release mechanism was installed to the main wing spar to ensure the structural integrity. A set of stability rods were designed and 3D printed to attach to the balloon side of the system. This limited the roll of the aircraft to guarantee a stable launch. The parachute system was iterated several times as it was critical to the recovery of the vehicle. The testing also occurred off the bridge of the AME building. Special attention was given to the storage of the parachute to make sure the system deployed smoothly. The parachute train contains a backup safety parachute and a reflector to make sure it is seen by other aircraft in case of a failure of the tether system. After all the systems had been tested reliably on the ground, it was time for flight. Here you will see a time lapse of the team's first ascent up to the desired release altitude of 400 feet. Once at the proper altitude, the vehicle releases. Once in the air, the team conducted investigation into the optimum flight paths required to obtain the maximum amount of power intake from the solar cells, increasing the endurance of the vehicle. The calculated banking angles and radius of holding patterns were input into an integrated autopilot system, and data was collected for further analysis. At the end of the flight, it was time to test the parachute system. The fiberglass canopy that the team has created is connected to a servo in the nose of the craft that is activated by a momentary switch on the ground controller. When the team is ready, the button is hit and the parachute is released. Special thanks to Dr. Sergey Shkrive, Adrian Buscella, Parisa Futoi, Dr. Jakan Tanga, and our classmate Sheldon Curley.